Hello students. In previous lectures we have talked about the neighborhoods of a point in metric space with help of OpenSPR. Now in this session we are going to study concept of the open set via OpenSPR. Okay, so open sets in metric space, very important concept in metric space. We are familiar with open intervals, union of open intervals, etc. Closed interval. I are calling them as open intervals. We'll get the idea about that by studying concept of open sets in metric space now. Okay, so we'll take a definition. Let XD be a metric space, then subset G of X, then subset G of X is open in X if G is neighborhood of X belongs to G for every X belongs to G. That is, if for every X belongs to G, there exists some R greater than 0 such that open pair about X with radius R is contained in G. Only concept of open neighborhood of a point is expressed here. So some books like R.R. Goldberg, real analysis, methods of real analysis, he's not talking about the neighborhood concept. He's just talking about open sets, because open sets, closed sets are important concept. Neighborhoods are not too much important. Okay. So now example, in RU, any open interval AB, AB for A less than B, open ray minus infinity to A and A to infinity for A belongs to R, are open sets. Phi R in RU are open sets in RU. Remember, RU means set of real numbers with respect to usual metric d of xy is equal to mod of x minus y for any xy belongs to R. That is the metric. Okay, these are the open. Now, while if I take closed sets, why AB is open? Okay, if I take AB now, AB on real line, this interval. If I take any x, so for x belongs to AB, there exists some R. What is R is equal to minimum of mod of A minus x or B minus x greater than 0 such that open sphere about this is contained in AB. Implies open interval AB is open in RU. Is it clear? This is your SRX is x minus r to x plus r is contained in AB. Right. So this interval or this interval that lies in open interval AB. Okay. Similarly, for open ray A infinity, for x belongs to A infinity, r is equal to mod of A minus x greater than 0. There exists r is equal to this such that open sphere about x, which is again x minus r to x plus r. This lies in A to infinity. So on this line, you can check that open ray minus infinity to A whole set R is also open. Why phi is not open? Why phi is open? I have to show that for any x belonging to phi, there exists open sphere about that which is contained in phi. But this statement must hold because phi contains no element. What is definition of not open? See here. A subset J of x is not open if there exists x belongs to G such that SRX is not subset of G for any r greater than 0. SRX is not subset of G for any r greater than 0. If I are able to find at least one point such that open sphere about x with any radius is not subset of G, it contains some points outside of G, then that x is not interior point of G, and that's why that set can't become open. That set can't become open. So for empty set, it is impossible to find some point such that open sphere is not subset of phi. It is impossible to find out that type of point in phi, and that's why phi is open. Okay. Now if I take some closed interval AB, okay. Note closed interval AB, closed interval AB, finite set not equal to phi, countable set, countable sets, closed rays, are not open in RU. If I take set of integers 0, 1, 2, 3 and so on, about any integer, if I take the open sphere with radius r, okay, SRN, even though that r is too small, it becomes open interval n minus r to n plus r, which is interval, and that interval is not subset of set of integer. Interval is not subset of set of integer, therefore set of integer is not open. Similarly, set of natural number, set of rational number. For set of rational number also, for any rational number x, if I take the open sphere about it, even though that r is very small, it is the open interval x minus r to x plus r, which contains rational as well as irrational number. That's why it is not subset of set of rational number. Same story is there for uncountable set irrational numbers also. So uncountable set irrational number is also not open in set of real numbers with respect to usual metric. Note this point, with respect to usual metric. U, usual metric, d of xy is mod of x minus y. That is very important. Okay. Next example, if I take, say, in discrete matrix space XD, every set is open. Set is open. So let A be subset of X. Then for A belongs to A, S half A is just singleton A, is contained in A. Then for any A belongs to A, S half A is singleton A contained in A, implies A is open in XD for any A subset of discrete matrix space. Okay, discrete matrix space. Remember this. Where d of xy is 0 for x equal to y and it is 1 for x not equal to y. Now in R2, U with respect to usual distance, if P is x1, y1, Q is x2, y2, then what is the usual metric? D2 of PQ is equal to under root of x1 minus x2 square plus y1 minus y2 square. That is the usual metric. Okay. In RU2 now. If I take, show that in R2 you show that line is not open. So if I take any line here in xy plane, if I take any point on this, say P, if I take even the very small neighborhood, okay, this is my SRP, is not subset of L. This story is for every point, but if you get just single point, then that set is not open. As line is not open, on same line you can show that circle or square, parallelogram, triangles are not open. But if I take now, say, this is my A, subset of R2. Subset of R2. Set up all points in triangle. What is my A set? A is equal to P. Say this is P belongs to R2 such that P is interior point of triangle. Interior point of triangle ABC. As in figure. Then is it open? Is it open? So if I take any point here, this is my P, arbitrary point. Then let R be, R is equal to minimum of, okay, distance of R1, R2, R3 greater than 0, such that R1 is equal to distance of P from BC line, R2 is distance of P from AC, and R3 is equal to distance of point P from AB. If I find distance of point from a line segment BC, line segment AC, line segment AB. This is my perpendicular. This is my perpendicular here. This is R1 and this distance is R3. Okay. Then among this R1, R2, R3, if I choose real number greater than 0, then SRP must be lies in triangle. Whatever my point from that triangle may be. So if I take interior points of squares, parallelogram, circle, okay, if I take circle here, some center C, and if I take P to be any point, then I can find its distance from center. Okay, this radius is R, this is your R1, then I'll choose this R2. What is R2 is equal to R minus R1. R minus R1. Then if I take the open sphere about P with the radius R2, then it must lies in that circular region. That's why interior part of circle is also open set. If I take set of all points in first quadrant, if I take all points in first quadrant, say this is my region, this is my E set. Again, same story is there. Whatever your point may be, I'll take a distance from y-axis, distance from x-axis. And which is the minimum among them? If I take open sphere about that point with that radius, minimum of these two distances, then that open sphere must lie inside that first quadrant. And that's why first quadrant, second quadrant, third quadrant, fourth quadrant are also open sets in R2 with respect to usual metric. Later on we are going to study that. I have defined three different metrics on R2 set, and all that metrics are equivalent metrics. So the aim is to study concept of equivalent metrics, etc. Okay. So now this is about the definition of open set and examples in open sets. Okay. Now we'll go theoretical part. Okay. Very important theorem. First important result from metric space now. Okay. So let XD be metric space. Whatever metric space, then 1 phi x are open in X. Are open in X. Second, union of open sets of X, union of open sets in X is open in X. Third, intersection of finite number of open sets in X is open in X. Okay. So first, to show phi is open. If phi is not open, then there exists some x belongs to phi such that SRX is not subset of phi for every r greater than 0. This is impossible as phi contains no element. This is impossible as phi contains no element. no element. Therefore, phi must be open in X. Now, for X belongs to X, for any X belongs to X, and R greater than 0, open sphere about X with radius R is equal to Y belongs to X such that D of Yx less than R, this is always subset of X, implies X is open. X is open in X. Okay. So we proved that phi and X are open. Okay. Now next one. Second. So let G alpha, alpha belongs to index set, be family of open sets, family of open sets in X. What is our aim? Union of G alpha. Alpha belongs to index set is open in X. So now let X belongs to, so this union may be union of finite number of open sets, maybe countable union, or maybe arbitrary union. There is no any restriction on choice of union of open sets. Okay. So let X belongs to G. X belongs to union of G alpha. Alpha belongs to index set. Then X belongs to G alpha for some alpha. For some alpha. Now since G alpha is open in X, implies there exists some R, therefore implies for X belongs to G alpha, there exists some R greater than 0 such that X open sphere about X is contained in G alpha. Okay. Moreover, and this G alpha is contained in union of all G betas. Beta belongs to index set. Is it right? G alpha is one among them. Okay. Thus, for any X belongs to G, there exists some R greater than 0 such that for any X belongs to union of G alpha, such that open sphere about X is contained in union of G alpha. This implies union of G alpha or alpha is open in X. So we proved that union of finite number of open sets or union of countable number of open sets or union of uncountable number of open sets is open. Okay. Now we have to prove that intersection of finite number of open sets is open. Okay. Third, let G1, G2 dot up to Gn be open sets in X. What is your claim? Intersection of Gi, I equal to 1 to n is open. Case 1, if intersection of Gi is equal to phi, then it is open. Then it is open in X. Case 2, if intersection of Gi is not equal to phi, then for x belongs to intersection of gi I equal to 1 to n, x belongs to gi for every I equal to 1 to n. Now since each gi is open, therefore for x belongs to gi, there exists Ri greater than 0 such that open sphere about x is contained in gi for every I equal to 1 to up to n. Choose R is equal to minimum of R1, R2 dot dot up to Rn greater than 0. Then SRX is contained in SRIX contained in gi for every I equal to 1 to up to n. SRX is subset of this, and therefore SRX is subset of intersection of gi I equal to 1 to up to n. Okay. Thus, for given x belongs to intersection of gi I equal to 1 to up to n, there exists some r greater than 0 such that SRX is subset of intersection gi I equal to 1 to n. Therefore, intersection of gi is open. In X. So what about the arbitrary intersection of open sets? What about arbitrary intersection of open sets? So note, arbitrary intersection of open sets need not be open. Justification. In RU, any open interval is open. Any open interval is open. Therefore, In is equal to minus 1 by n to 1 by n is open in RU for each n belongs to n. Now intersection of n is equal to 1 to infinity. What is I1 interval? Open interval minus 1 to 1, I2 is minus half to half, minus 1 by 3 to 1 by 3. So if I take intersection of first 10 open intervals, then it is I10. Intersection of 1 lakh interval, it is I1 lakh, that is minus 1 upon 1 lakh to 1 upon 1 lakh. So size of that interval goes on decreasing. And as intending to infinity, this is singleton 0. Okay, is not open in RU. So thus, here we proved that in any metric space, empty set and whole metric space are always open. Then arbitrary union of open sets is open, finite intersection of open sets is open. Later on, we are going to prove that every open sphere is also open set. Every open sphere is also open set. That is our next aim. To prove that every open sphere is open. Now, in higher level, you have the concept of topological spaces. If X is an empty set, then tau collection of subsets of X is said to be topology for X if phi and X belongs to tau. Phi and Okay, X is non-empty set. Tau is collection of sets U subsets of X. Then this tau is a topological space, topology for X if first phi X belongs to tau, second union of UIs, U alphas belongs to tau, and intersection of UI I equal to 1 to n belongs to tau. Okay. So collection of subsets of X is said to be topology for X if phi and X are in tau. Second, arbitrary union of subsets of that tau is again subset of tau. And third, finite intersection of members of tau is again in tau. Then that collection is called as topology. And then each of these sets in this collection tau is called as open set. It's called as open set. So every metric space, according to this theorem, is always topological space. Every metric space is always topological space. So this is the basic for topological spaces. Every metric space is topological space, but converse is not true. Topological space need not be metric space. Our aim is not to study topological spaces. Our aim is to study concept of metric space. Okay, but topological space depends on this. So with this discussion, today we'll stop here. We'll continue in next session. Till that, stay at home and be healthy. And try to enjoy this online teaching. I also request some of the viewers are not observing all lectures. If you have to understand this metric space course, you have to start to listen each and every lecture from first lecture continuously. Otherwise, if you listen the first lecture and if you go to the fifth session, then it is difficult to understand because there is a sequence from topic to topic. So my suggestion is that please go through all topics, all sessions to understand metric space in depth. And also I request, please like the session and try to subscribe this channel so that I will also get energy to prepare this e-content material for you. Thanks.